This video is the notes on simplifying radical expressions. First of all, let's look at some vocabulary that we have. If we have this expression, the cubed root of x, the symbol is called the radical. The little number 3 that's inside the radical is called the index, and the x, or the thing that's underneath the radical symbol, is called the radicand. You need to know these vocabulary words so that when we talk about them, you know which things we mean. A radical expression is simplified when anything that can come out from under a radical is out, and any terms that can be combined are. There is never a fraction left under a radical or a radical left on the bottom of a fraction. That's what happens for something to be simplified. To simplify a radical, we have a few things that can happen. For a single radical, we want to start out and think of the radicands, that's the part underneath the radical. Think of their factors. They are like the radical's prisoners. To escape from underneath the radical, they need partners. The number of partners needed to escape depends on the radical's index. That was the little number inside the radical. To escape from under a square root, 2 partners must work together to form a team. To escape from a cubed root, 3 partners must work together to form a team. Once they form a team, they are like a single factor on the outside. If there are not enough team members under the radical, a factor cannot escape. We're going to try to use this example to set up some of the things below where we're simplifying radicals. In example 1, we're simplifying the square root of 80. When the index is a 2, we don't need to write it. But we know in order to simplify the square root of 80, we need to have at least 2 of the same factor to come out from underneath. I'll start out by making a factor tree for 80. I can break 80 down into any 2 of its factors. The first 2 I think of are 8 and 10. 8 I can then break down to 2 and 4. 4 I can break down to 2 times 2. 10 I can break down to 2 times 5. At this point, all of the ends of my factor tree are prime numbers. They can't be broken down anymore. In order to take something out from underneath a square root symbol, I need 2 to make a partner. I have 2 2's, so I can take a 2 outside of my radical. I have another set of 2's, so I can take another 2 outside of my radical. These are factors, so everything is multiplied together. At the end, I still have this 5 without any partners. It cannot escape, so it's still left underneath the square root. In the final step, I want to combine my terms on the outside. 2 times 2 is 4. I still have the square root of 5 left underneath, and the square root of 80 simplified is 4 square roots of 5. In example 2, there's already 4 on the outside. So I have my 4 outside, and then I want to try to break down 54 by making its factor tree. Pause the video while you try number 2. To break 54 down into its prime factors, I have 3 3's and a 2. So I have a set of 3's. I need a set of something to come out from underneath the square root. Unfortunately, both the 3 and the 2 are still left inside because they don't have any partners. Now I just need to put each of these parts together. On the outside, I have 4 times 3, which is 12. On the inside, I have 3 times 2, which is 6. So my simplification is 12 square roots of 6. In example 3, I have 2 different radicals that are being multiplied together. When I'm multiplying radicals, the outsides go together, so my 7 times my negative 3 is negative 21, and my insides can be multiplied together. I have the square root of 6 times the square root of 10, which is the square root of 60. Since my next step is going to break the 60 down, I could have just left it as 6 times 10 if I didn't want to do the multiplication in my head. 6 breaks down further into 2 times 3. 10 breaks down further into 2 times 5. Now I'm looking to see at what I can bring out. One of the most common mistakes we make is we forget to leave this 21 outside there when we're taking things out. So be sure and keep that out there. Next, I have two 2's, so I can take a set of 2's onto the outside. Then, underneath my square root, what am I going to have left? I have a 3 and a 5 that don't have any partners, so they need to stay inside. On the outside, my final step, put everything together. Negative 21 times 2 is negative 42. Underneath the square root, I have 3 times 5, which is 15. And my radical has been simplified. In example 4, I have a slightly different situation because in this one I have an index of 3. Remember, the index was this little number in here. That means the cubed root of 54. I'm going to start out, I'm going to do my prime factorization for 54, just like I did in the earlier problem. But this time, in order to take something out from underneath a cubed root, I need to have 3 partners to form a team. I have 3 3's, so I can take a set of 3's out. I only have 1 2, so that 2 is left in. To simplify the cubed root of 54, my answer is 3 times the cubed root of 2. Pause the video while you try to simplify example 5, the 4th root of 80. Remember, to take something out from underneath a 4th root, we're going to need 4 partners to form a team. When I break down 80, I have 2 times 2 times 2 times 2 times 5. So I have 4 2's. I need a set of 4 for one of those 2 groups to come out from underneath my 4th root. I still have a 5 that didn't have any partners, so it stays inside. And the 4th root of 80 simplified is 2 times the 4th root of 5. I'm going to use the same philosophy with numbers as I will with letters. If I'm trying to simplify in example 6, the square root of 81, p to the 4th, q to the 3rd, I'm going to start out and write down my factor tree. 81 is 9 times 9, and the 9's break down to 3 times 3. We wouldn't have had to finish this factor tree if we didn't want to. I have 2 sets of 3's which I can take outside. You also might have noticed in the beginning of the problem that the square root of 81 was 9, and you could have just taken that out in the get-go. So let's look at what we have with our letters. P to the 4th. P to the 4th is P times P times P times P. Q to the 3rd, Q times Q times Q. Hopefully we won't have to write these out forever, but it might help us see what's going on in the first example. In order to take a group of P's out, I have to have 2 of them. So I have 2 groups of P's that I can take on the outside. I'll write this in my final answer as p squared. With my q's, I have 1 set of q's that I can take out, but I'll still have a q that's left inside. So my final answer is 9p squared q times the square root of q. In order to take things out from underneath the 4th root, I'm going to do the same thing. I just worked down the 4th root of 81. 81 I know is 3 to the 4th power. Oops. Hold on a second. That was a 4th root. Another common mistake we make is forgetting to write down the index, so don't forget that when you're working your problems. 81 is 3 to the 4th. Then we have m to the 4th, and we have n to the 5th. I'm trying to decide what needs to come out from underneath the radical. I wrote this one this way so that we could see anytime we have an exponent that's 4 or larger, that means it's going to be able to come out from underneath the 4th root. If I listed my factors out, I've got 4 3's, so I can take a 3 out from underneath. I've got 4 m's, so I can take an m out from underneath. And with the n's, I've got 5 n's. I should realize without having to write them all out that if I have 5 n's, I can take 1 n out and I'll still have 1 n left underneath. Remember, this was a 4th root, so I need to be sure to put that 4th root in my index. If we're multiplying roots together, it's very important that they have the same index. If these didn't have a cubed root with both of them, we wouldn't be able to put the things together right now. So I have a 7 on the outside, I have a 4 on the outside. Underneath my cubed root, I have a 27 and an 8. I'm not going to bother to multiply that together because I know I'm just going to factor it back down. I also have n squared times n, which is n to the third power. On the outside, I have 7 times 4, which is 28. On the inside, I have 27. We should recognize without making our factor tree that 27 is 3 cubed, so I can take a 3 out. We should also recognize that 8 is 2 cubed, so I could take a 2 out. If you didn't, just break them down by dividing. The cubed root of n cubed is just n because I had one group of 3 that I could take out. In this problem, everything was on the outside. There was nothing left underneath without a partner. My final step is to combine 28 times 3 times 2, which is 168, and I had the one n. I don't need to write the empty cubed root symbol because there was nothing underneath. In example 9, we have a fraction. It's important for us to realize that if we have the square root of a fraction, like the square root of x over y, that's the same thing as the square root of x over the square root of y. It doesn't matter how we write this. They're both the same expression. So we can't leave this the way it is because right now we have square roots on the bottom of our fraction. The first thing I should always try to do in this case is see, is there something I can reduce without thinking of the radical, just thinking of the radicand or what's underneath? Can I simplify that fraction? 125 divided by 5 is 5. So I can reduce a 5 out of the top and the bottom. X cubed over x is x squared. So I can reduce the x out of the bottom. Now all I really have to do is simplify. Oops, this was not 5. This was 25. First, I want to see, can I simplify this fraction? 125 is divisible by 5, so ignoring the radical on the outside and just simplifying the fraction, 125 over 5 is 25. Essentially what I did here is I divided 5 into the bottom one time, 5 into the top 25 times, and that reduced to 25. X cubed over x is x squared. Essentially what I did here is I said x goes into x one time. I could take one of the x's off the top, which would leave me with x squared on the top. But remember, this was all still underneath our square root symbol. Now I want to see, can I break this down further? The square root of 25 is 5. Hopefully we don't need to do a factor tree for that, but I can see that 25 is 5 times 5, so there's one set of partners to come out. The square root of x squared is just x, so I'm going to bring that out. In this class, we're going to assume that the square root of x squared is x. In actuality, we have to worry about whether x could be positive or negative, but we're not going to worry about that. We're going to say all variables in this class are positive, so we don't have to worry about it. So, number 10. In this one, we want to see, can we simplify our fraction? Well, yes, 5 goes into 320. How many times does 5 go into 320? It goes in 64 times. How about m to the 7th over m to the 3rd? M to the 7th over m to the 3rd is m to the 4th. So I'm dealing with the square root of 64 m to the 4th. We shouldn't need a factor tree to realize the square root of 64 is 8. The square root of m to the 4th, if I listed all my m's out, I would have 4 m's. So I'm going to have two groups that are able to come out, and I'll have m squared on the outside. Again, nothing was left underneath. Unfortunately, not all the time is everything going to come out from underneath. In example 11, we can't reduce the 17 and the 5. We should realize, however, that this is the square root of 17 over the square root of 5. The problem with this expression is that we're not allowed to leave the square root in the bottom of the fraction. You may remember from the past, the way we get rid of this is to rationalize the denominator. I need to multiply the bottom of this fraction by the square root of 5 so that I'll have two 5's underneath and be able to take them out. However, I can't multiply a fraction by 1 over the square root of 5. I can only multiply a fraction by 1. So I need to multiply my fraction by the square root of 5 over the square root of 5, which is really just 1, and anything times 1 is still itself. So now on the top of my fraction, I have the 17 and the 5. I'm just leaving them that way as 17 times 5 right now because I'm going to try and break it down anyway. On the bottom, the square root of 5 times 5, that's the square root of 5 squared, or the 5 will come out from underneath. Well, I tried to leave 17 and 5 separate, but since they're both prime numbers, nothing else is going to come out. 17 times 5 is 85, and I have to write my final answer as the square root of 85 over 5. Pause the video while you attempt number 12, where you need to rationalize the denominator to get rid of that square root of 7 on the bottom. In number 12, I multiplied the top and the bottom by the square root of 7. 19 was a prime number, so there was no use in trying to break it down. 19 times 7 was the square root of 133, and on the bottom, the square root of 7 times the square root of 7 was 7. On the back of the paper, we now have radicals with addition and subtraction. We should remember from Algebra 1 that in order to combine two radicals, they must have like radicands. In other words, we can treat the square root like a variable. This one has 2 square roots of 2 minus 2 square roots of 2, and then we have 3 square roots of 3. Square roots of 2 and square roots of 3 are not like terms. The square roots of 2 are like terms, so 2 square roots of 2 minus 2 square roots of 2 is no square roots of 2, and that's 0. I'm not going to write anything down for that. My 3 square roots of 3 cannot be put together with my square roots of 2, and my final answer is just 3 square roots of 3. In number 14, on initial inspection, it looks like none of these are like radicals because I have square roots of 20, square roots of 25, and square roots of 80. But first, I can simplify these. I can break the square root of 20 down. I had a 2 that was already on the outside. Then I'm going to group another 2 that I can take out and a 5 that's still left underneath. For the square root of 25, I can take a 5 out. I already had a minus 2 on the outside, then I have my 5 that I take out. In my next term, I had plus 3, and now I'm going to break 80 down. When I break 80 down, I have 2 2's that I can take out because I have 2 sets of 2's. And I still have the 5 left underneath. So in this expression so far, I have 4 square roots of 5 minus 10 plus 12 square roots of 5. Now I'm ready to put my like radicals together. In this one, my like radicals are square roots of 5. I have 4 square roots of 5, and I have 12 square roots of 5. If I treat the square root symbol like a radical, 4 of something plus 12 of something is 16 of the same thing. So the square root of 5 doesn't change, just the numbers on the outside do. I still have my minus 10 that can't be combined because it doesn't have any square roots of 5. Pause the video while you try number 15. Realize square roots and cubed roots cannot be like terms. So in this one, we're going to simplify first and then see what we can put together. In my final answer for number 15, I have a 12, which has no radicals. I have minus 8 square roots of 3 and plus 6 cube roots of 3. Square roots of 3 and cube roots of 3 are not like radicals, so they cannot be combined. In number 16, I have 2 square root of 6 minus 3 square root of 2 times 3 plus the square root of 2. In this expression, I want to FOIL or do boxes. I can treat it just like a polynomial. Two square root of 6 minus 3 square root of 2. And then I have my 3 plus the square root of 2. In my first box, 3 times 2 square roots of 6 is 6 on the outside and 6 on the inside. For my next one, it's going to be a plus because they're both positive. I have 2 on the outside, and I have 2 times 6 on the inside, which is 12 on the inside. Down here, I have a minus. I have 3 times 3 on the outside, which is 9, and I have a 2 on the inside. And on the end, a negative times a positive is a negative. 3 was the only thing on the outside. On the inside, I have the square root of 4. We should realize either now or when we go to write this term out that the square root of 4 is just 2, so this box down here is really 3 times 2, which is negative 6. I'm going to go ahead and write my terms out now. I have 6 square roots of 6 plus 2 square roots of 12 minus 9 square roots of 2 and a minus 6 on the end. I also should realize that with my square root of 12, I can break that one down into 2 times 6. 6 was 2 times 3, so from that one I can take a 2 on out. So now we have 6 square roots of 6. I have my 2 taken out with the 2 that was already under there, so I have 4 square roots of 3 minus 9 square roots of 2 and a minus 6. None of these can be broken down any further. Since 6 is just 2 times 3, I can't take anything out from there, and I'm done with that one. Pause the video while you try number 17. This is a special problem because my 2 expressions are the same with the exception of the sign in between them. One is minus and one is plus. They're called conjugates. That's a word we'll use later in the rest of the unit. Conjugates are 2 things that have the same 2 terms, except they have opposite signs in the middle. In this one, when I multiply my 2 conjugates together, the square roots in the middle expression cancel each other out to 0. From the first part, because it was a square, I won't have any square root left, and that was just 45. And on the end, I had a perfect square, which was minus 16. And I put those 2 together. 45 minus 16 is 29. When I multiply 2 conjugates, my answer will always be a nice real number like the square root of 29, or like 29, sorry, no square roots left. It will always be rational, a nice number with no square roots. In number 18, the biggest mistake we make with this one is we try to distribute the squared. Remember that 4 minus 2 square root of 3, the quantity squared, means 4 minus 2 square root of 3 times 4 minus 2 square root of 3. I can do this multiplication using my boxes or by FOIL. Either way, when I work it out, I'm going to wind up with 16 minus 8 square roots of 3 minus another 8 square roots of 3. And then on the end, I had 4 times the square root of 9, which the square root of 9 is just 3, so I can write that down as 4 times 3. Then I'm going to start to simplify the rest. My 16 was already simplified, and then I had my 8 square root of 3 and my 8 square root of 3, so I can put them together to make 16 square roots of 3, and on the end I had 4 times 3, which was 12. Finally, my only like terms are my 16 and my 12, which I can add together to get 28, and my minus 16 square roots of 3 have to stay separate from them. In number 19, I want you to try and simplify the square root of 8 and the square root of 18 first. Then, multiply using boxes or FOIL to simplify the expression. Pause the video while you give this last example a try. I simplified the square root of 8 to 2 square roots of 2 and the square root of 18 to 3 square roots of 2. Then I multiply these 2 binomials together using boxes. When I do that, I have 20. In my middle, I have minus 15 square roots of 2 and also plus 8 square roots of 2, which I'll put together in just a second. And my last term was minus 6 square roots of 4, which is 6 times 2, or really minus 12. So I have 20, and my minus 12 from the end can go together to make 8. And then I have minus 15 square roots of 2 plus 8 square roots of 2, which simplify to minus 7 square roots of 2. And that is my final answer.